Composing and resolving vectors then. Composing means putting together, resolving means breaking apart. Really? So why do we have to do this? Well, vectors, unlike scalars, have got direction. You can't quote a vector correctly unless you quote its direction as well. So if you had an object with a force in that direction and a fourth force in that direction, you couldn't just add them together directly. You'd have to say this 5 has a component in this direction and this 5 has a component in this direction. That is to say, this 5 is partly horizontally to the right and partly vertical. So you have to break this up into the bit that's acting vertically and the bit that's acting horizontally. This is your resolution. So how do you do that? Well, your 5 Newton at some angle theta has the same effect as these two. Call that horizontal and call that vertical. There's my 5 newtons and there's my angle. So if we look at our right angle triangle here, we have sine of theta would be this over 5 and cos of theta would be this over 5, and so V would be 5 sine theta and H would be 5 cos theta. So just a quick word on why this is useful. Your horizontal and vertical, or if we were to take a jump ahead and say forces which are at right angles to the slope and forces which are along the slope, vectors which are at right angles to each other have no effect on each other. So you can add all the verticals together and completely ignore the horizontals. You can add all the horizontals together and completely ignore the verticals. So you would say in this example here, you would have vertically, you would have 5 sine theta minus 7. There's vertically. And horizontally, well, the 7 doesn't have any effect. So horizontally, you've got 5 cos theta. So then you can say, I've got 5 sine theta minus 7 that way, and I've got 5 cos theta that way, and the resultant of those two, by composing those together, is in there. And if I just say that's V and that's H, R of course is the square root of V squared plus H squared in this case. Clearly this V and this V, this H, well, this V and this V are not the same. So this is the resolving bit. This is the composing bit. Now, that's all very well, and you can do the whole sine and cos thing by looking at the triangle. But when it comes to forces on slopes, it's a bit more difficult to see the triangle that you have to make. If we take a force F at an angle theta to the horizontal, If you imagine rotating through the angle to get to the component, so in order to get from here to the horizontal component, I'm rotating through the angle to get there, then that component will be the cos component of f. If you rotate away from the angle to get the component, and of course this and this are the same, then it's the sine. Now, that little rule always works. And if we were to take it to a more complex example, let's imagine we had now, it makes sense to resolve along and at right angles to the slope here, because I've got friction acting down the slope, so that's parallel with the slope. I've got the normal reaction at right angles to the slope. So to resolve along and at right angles to the slope makes sense. So what are the components? Well, that's theta. That, of course, is 90 degrees because that's vertically down and that's horizontally. So that angle in there is 90 minus theta. So I want the component of the weight down the slope. And I say to myself, well, I've got to rotate mg through 90 minus theta. So it is mg cos 90 minus theta, which is, I'm sure you know, mg sine theta, because the cos of 90 minus theta is the same as sine of theta. So that makes this kind of scenario much easier to work with, because I'm not trying to draw a triangle. And deciding what triangle to draw can be tricky. A worked example on this composition resolution business. So let's take an object. Let's say it has a mass of 100 kilograms, so there's a force of 100 g newtons is the weight. And we have a reaction R, and we have a force of, let's say, 1000 newtons acting at an angle of 30 degrees this way. And let's say we have 600 newtons acting this way. So let's say we have if we resolve vertically, we would have R minus 100 times 9.81, which is that, plus the component of the 1000 vertically, well, that's 1000 sine 30 degrees, because if you remember what I said was we want the vertical component, so we have to rotate away from the angle to get to the vertical, and that means we use the sine of the angle. So if we're going to say that there is no vertical force, let's just say this thing is not accelerating in the vertical direction at all, then that has to equal 0. So then we can say R equals minus 1000 sine 30 plus 100 times 9.81, because I'm taking this to this side of the equation, which means I change the sign to plus. I'm taking this to this side of the equation, which means I change the sign to minus. So that gives us our value for r. Now, sine 30 is 0.5, so there's minus 500 plus 98.1. So there's minus 401.9 newtons. And that is, of course, because we have taken down as positive. So R then is 402 newtons to 3 sig figs vertically. So to 2 sig figs, 4.0 times 10 to the 2 newtons. If we then resolve horizontally, we have 100 cos 30 degrees minus 600 is our resultant force horizontally, unless of course 100 cos 30 ended up being 600, which it won't. The cos of 30 of course is root 3 over 2. So we have minus 513.4 newtons, so we have 513.4 newtons to the left. And so if we, for example, wanted the acceleration of this, we'd say, well, Newton's second law, F equals ma. We have established that there is no, or our condition was there was no vertical force, so that it wasn't accelerating in that direction. So horizontally then, we have a force of minus 513.4 acting on 100 kilograms. That's our acceleration. So our acceleration then is minus 0.5134, which to 2 sig figs, we could do to 3 sig figs, is minus 0.513 meters per second squared. And I should have done that to 3 as well. So 4.02 times 10 to the 2.